Yeah, so let me just remind you quickly what we said so far about this non-isometric holographic map. Okay, so we were working with a simple model where we defined a map V, which went from the degrees of freedom behind the black hole horizon in the bulk to some boundary description or fundamental description of the black hole. And we said that after the page time, this is some non-isometric map, which is given by this form, where you act with some typical unitary from the Haar ensemble. And then in the output, you have the system B, and then the remaining part of the output you project onto some reference state 0 in some system P. Okay? And let me just remind you some results that we stated or derived about this map. Okay, so the whole map was from LR and tensored with the radiation system in the bulk, and it acted as VLR times the identity on the radiation. Okay, and two things that we said were true were that if you calculate for some input state rho LR, if you calculate the entropies of the resulting state sigma, including the radiation system, then you find that the boundary entropies will be consistent with the QES formula with islands. Okay, so in particular, if your input state in the effective picture has the form of Hawking state, where, say, you have some pure state on the L degrees of freedom, and you have a maximally entangled state between small r and capital R, then you find that if you map this to psi tilde in the fundamental description by acting with V, then the entropies of psi tilde will be of the form in both the B system and in the R system. The entropy will be given by the minimum of log B log R. Okay? So in particular, after the page time, the entropy will be given by this log B, which can be seen as the contribution of the island in the QES prescription. Okay, so that was one thing that we found, that the entropies are consistent with the QES formula. And then the second thing that we showed last time was that the overlaps between a large set of states in the input, and in particular the set of sub-exponential states, can be preserved with high probability. Even though this map seems to have a lot of null states, it can approximately preserve a surprisingly large number of inner products. Okay? So, so today we'll be talking about a third aspect of what you can show with this simple model, which will have to do with the reconstruction of operators in the bulk or effective picture as operators in the boundary picture.
So the first thing is some combination of your first lecture and how?
Yeah, the first thing I stated in my second lecture but didn't explicitly derive.
Okay.
That would follow from using the averages of the Haar averages of U times U dagger to the power of n, because you can calculate this for the nth Renyi entropy, and then analytically continue to 1 for the von Neumann entropy. Yeah, but it is a little bit, the calculation looks like the one in the first lecture.
Right.
Yeah, but this.
And in particular, is there like a way to make it, like, put it in the language of your first lecture?
Yeah, we discussed this last time. So not exactly, because here this map has the interpretation of a map on a single spatial slice, whereas
There's no time evolution.
yeah, although I guess there is a dynamical version of the model where this non-isometric map can be seen as coming from the time evolution, and in that case you could say something like that. But yeah, not from what I've told you so far.
Sorry, this is what I was about to ask. Maybe this is something stupid, but this why is there an a priori expectation that U should be some effectively random unitary?
Yeah, this is based on the idea that the bulk-to-boundary map in holography is something complicated. And in the past, things like tensor networks of random tensors have captured a lot of.
I mean, there's this thing perfect in tensors also, right?
Yeah.
Where there's no randomness, but still captures many features.
It captures many features, but I think somehow, I don't remember, there are some aspects of the random tensors which are better than perfect tensors. Like, I'm not sure in the perfect tensor case if you, I don't think that you get a bulk entropy type of term in that case. Anyway, but maybe you do, but yeah, but I guess based on the fact that random tensor networks tend to work, this is the simplest random tensor network you can make for a holographic map from the bulk to the boundary. And then it's justified, you can think of it as being justified by the fact that it produces a QES formula, and it's the simplest model which can do this.
In random tensor networks, you sort of make the tensor network out of small random tensors.
Yeah.
Whereas here you have a very big random.
Yeah, exactly. And that's because we wanted to do the simplest possible thing. But somehow it is the random average in both cases which gives you the QES formula. And also, yeah, if we had, yeah.
Sorry, can I ask something here, if you don't mind?
Yeah, yeah.
I mean, I thought the idea here is that it's sufficiently generic, unitary, as long as it's in a big enough Hilbert space, is going to be approximated at least for many things by taking a random average. Because, you know, it's sufficiently generic. That happens for some things. I don't know. Can one justify it here, doing the random average in that way?
Yeah, in this case, it's definitely taking away a lot of the local structure of the bulk spacetime, which is correctly captured by the random tensor networks. You can make a random tensor network model for this evaporating black hole setup as well. It would be pretty analogous to what they have in the in this paper from 2017.
I mean, not getting into random tensor networks, just in terms of a unitary operation. Let's say you're getting your non-isometry by taking some unitary operator and then doing a projection, right? If I understood.
Yeah.
So if I took a generic, a unitary, and all dimensions are big, will its action be captured up to small corrections by doing a random average, or no?
Yeah, it will, and that is exactly the point of the measure concentration results from last time.
Okay, so then that tells you that I haven't absorbed that, but that's what I was thinking. So then you don't have to say that you are doing a random average, right? You just have a generic unitary,
yeah.
Your results will go through.
Yeah, but it's not something very simple because, yeah,
So
sorry.
I was going to say that, I mean, even in that case, I would ask why is it a generic unitary and why is it not a special unitary?
Mm-hmm.
Because one suggestion, for example, you know, proposes it to be this perfect tensor is some very specific unitary.
Mm-hmm.
So I'm just, a priori, I'm asking why is there some expectation about this unitary? Thermalization has some nice, you know, some motivation, but this is not of that type, right? But you also mentioned these words that there is a way of thinking about it,
Yeah.
in which case it becomes some sort of a evolution type operator.
Yeah, you can see it as coming from the boundary time evolution as well, and in that case, it's more clear why it should be random looking. If I have time, I can try to talk about that at the end.
But I mean,
Yeah, that could be one way of thinking about it.
Yeah, you should go on, but Abhijit, I mean, in my mind, this is some huge, clearly some, sorry Shreya, huge caricature of what might be going on in space-time, right? And at least if the cartoon works for a generic U without evoking some very special U, then you might hope it captures as a cartoon what's really going on, right, in space-time. I mean, if it was some very fine-tuned U, then you would say, hey, string theory better produce that U, otherwise I'm not going to trust anything Shreya says. But the fact that it's generic may actually go in the direction of us saying, okay, at least in general, it could be capturing something going on in terms of the specific U that string theory might be generating. Isn't that the sort of spirit of the discussion, Shreya? Just asking.
Yeah, I think that's reasonable too. I mean, it definitely shouldn't be. Yeah, but clearly it does. Yeah, like it doesn't capture any effects of spatial locality within L or within R in the bulk geometry. So yeah, so it is missing some things, but
Anyway, sorry. Please go on.
yeah. No.
No, I understand your points.
Yeah, okay.
Sorry, can I ask?
Yep.
I might have forgotten, but in the first lecture review, where was it important that this U was a time evolution operator, or that it was not just summing to?
Because we were trying to use the fact that the system is chaotic, and then for a chaotic system, you expect that the time evolution operator should have certain properties, like it should look roughly random. In this case, so far this doesn't have the interpretation of a time evolution operator in a chaotic system. It's just the map from the bulk to the boundary. So
you're saying it was important to say that U is random?
for the calculations that we do here as well, it was important that U was random. But that is motivated more by the idea that the bulk to boundary map in holography shouldn't be something extremely simple. Like there isn't a one-to-one mapping of the degrees of freedom from the bulk to the boundary, and in general you have the sense that it's something complicated, but yeah.
I think I've asked this before, Shreya, but does it have to be like a truly R-random operator, or can it be like a 2-design or 3-design?
For the measure concentration results to be true, it needs to be a random operator.
Okay.
Because for 2-design or so on, you don't have these measure concentration. I think some people have shown weaker measure concentration results, like maybe you can show polynomial suppression of fluctuations, but that's not strong enough to give us the statements that we want.
But these two statements here?
The
first one.
Yeah, this is definitely still true. If you have an n design, then you can show it for the nth Renyi entropy. And then you can, for this reason, if you have some random tensor network made out of local things, then again you can show this first statement. For the second statement, you need to use measure concentration, so that you can't show. But then again, you can show on average. Like we started by saying that the average in a product is preserved. The fluctuations around the average are small. Those things would still be true for these other cases. Okay, so this was a summary of what we did so far.
Let me ask you.
Yeah.
That's probably a very stupid question. You told us last time that this projector, that you can build the most general linear map, perhaps, from something like this by taking a projector.
Mm-hmm.
And now, physically, we expect this map from this. Is there a physical reason to expect this map from this bulk Hilbert space to the boundary Hilbert space to be linear? I mean, probably the answer is obviously yes, but just articulate.
Yeah, I guess this would be based on the idea that like it would then map linear operators to linear operators, and if you have a superposition of states, I don't know, like these are all things which
it's just nice.
It's just nice, yeah. Like,
thank you. But I was wondering, would there be a paradox if there was not? Could you argue that it had to be?
Linear bulk evolution maps to linear boundary evolution because of this effect.
I suppose.
If it were not, the linear bulk evolution would map to boundary.
Yeah, so you're saying that, fine, sounds good.
mm-hmm.
Sounds good.
Okay, so now we want to talk about reconstruction of operators. So V was a map from.
Sorry, so you're saying that even though we don't really know in ADS-CFT what this U is, that it has this structure has to be the case.
Just that it's a non-isometry.
That it's this kind of map that you take a unitary to some larger space and do a projection.
Yeah.
That has to be the right
Yeah.
structure.
Yeah. Okay, so let me first just talk about what I mean about operator reconstruction in the more general setup where V could be an isometry. In fact, let's start with the case where V is an isometry, because that is what we usually think about. So V is a map from H effective, which is the Hilbert space of bulk excitations about some fixed boundary geometry, which doesn't have a black hole. So it's a map from this to the fundamental description. Okay, and so I have some states psi in the bulk description, and then they map to psi tilde in the boundary description. So now if I have some operator O acting on the effective Hilbert space, then I define O tilde as the reconstruction of O on this H fundamental if it obeys two conditions. So let me write them down. So O tilde acting on the state V psi, so the state psi sent to the boundary description, should be the same as if you were to act on psi with O in the bulk description and then send the resulting state to the boundary. Okay, so this seems like a very reasonable condition for reproducing the action of O with O tilde in the boundary. And then a second condition will be that I can reproduce matrix elements of O in the bulk using matrix elements of O tilde in the boundary. So this is just saying that psi 2 tilde, O tilde, psi 1 tilde is equal to psi 2 O psi 1. Okay? In the case where V is an isometry, I can immediately write down an operator, given some O, I can immediately write down O tilde, which satisfies these conditions, which is just O tilde is V O V dagger. Okay, so then just from the fact that V is an isometry, both of these are satisfied. So from just writing it down this way, it seems like it's not obvious that there is any local structure to this statement. So it seems like if I have some bulk operator O, even if it's some local operator acting in some region, O tilde could be something which is spread out in some non-local way in the whole boundary. Okay, but it turns out that a stronger statement can be made about reconstructions of operators, which is called entanglement wedge reconstruction. So for this, let me so for this, let me remind you of the definition of an entanglement wedge, which I mentioned in the previous lecture, or in the first lecture. Okay, so we're going to define something called a quantum extremal surface. And it will be associated with some bulk state rho and some boundary region A. Okay, so if I have some boundary region A, and in the bulk I'm in some state rho on some bulk geometry, then I can define a quantity. I can consider all possible surfaces sigma, which are anchored on the endpoints of A and go into the bulk. And then I can define a quantity called the generalized entropy, which is associated with rho, A, and sigma. And it's given by the area of sigma over 4g Newton plus the bulk entropy of rho in the region small a, which is enclosed by sigma and A. Okay, and then for a given rho and A, I can find the surface sigma min, which minimizes this generalized entropy, and then that is called the quantum extremal surface. Okay? And then the corresponding region A for that will be called the entanglement wedge of A in this particular state. So one thing that I mentioned that we've been assuming throughout is that if sigma is the boundary state, if small sigma is the boundary state corresponding to rho, then the entropy of sigma in capital A will be given by S gen of rho A sigma min. And notice that out of these two terms, in cases where you don't have a black hole, in most such cases, this bulk entropy term will be much smaller than this first term, which is proportional to 1 over g Newton. So in such cases, for all states in the effective Hilbert space, this sigma min will be some fixed surface. Okay? For this context, it was shown in a series of papers, in particular very explicitly by a paper by Daniel Harlow in 2016, that this statement is equivalent to a second statement, which is that operators in small a or small a bar can be reconstructed entirely on capital A or capital A bar. Okay, so so this is saying that it's possible to find some reconstruction which works on the entire effective Hilbert space in these cases, which if I had a bulk operator, which was some local operator in small a, then it'll live only in capital A. Okay, and so these two statements were shown to be equivalent to each other, and the second one is referred to as entanglement wedge reconstruction. Okay, so it turns out that that all of these things will be more problematic in the non-isometric case, which you might guess because a lot of the statements that we made here relied on V being in an isometry. Okay, in particular, even for this global reconstruction O tilde to exist, something like this can't exist if, for instance, you have some psi which is not a null state of the map V, so it's not being sent to 0, but then you act with some O on psi, and after you act with O, it maps to some null state. So then an equation like this doesn't really make sense because it would tell you that O tilde should be 0, but such an O tilde which is 0 would never be able to reproduce these matrix elements. Okay, so definitely for the non-isometric case, it seems like you just can't have a statement like this for all possible operators and all possible states. Okay, and you could try to ask, because it seemed like the statement about inner products worked very well on average and fluctuations about the average were small, one thing that you could try asking in this setup is if this, if a reconstruction like this works on average, if you average over all possible U's, then is a statement like this still true? So for instance, is the distance between these two states small or exponentially small in B if you average over all possible U's? And you find that even something like that is not true in this case. Okay, so so in particular, if I try to do some reconstruction like O tilde, if I try to take this to be some operator OLR, which lives behind the horizon, then this does not work on average. Okay, and then another thing that is confusing about this setup is that because the bulk entropy term in the QES formula and the area term could both be comparable to each other, because the number of degrees of freedom is of order 1 over g Newton. So different states in the effective Hilbert space have different QESs. So in particular, if I consider the Hawking state, then I have the QES, which is just inside the black hole horizon, and that gives me an island contribution to the entropy, and suggests that I should be able to reconstruct operators which are behind the horizon in the radiation of the black hole. But if I could have considered a different state in this Hilbert space, which was just a product state between the interior of the black hole and the radiation. And for this product state, the QES of the black hole would contain the interior of the black hole. Okay, so in this case, I would say that operators which are in the interior should be reconstructed on the black hole. So somehow in this case, you're not going to have a statement of this kind for all states in the effective Hilbert space. Okay, does that seem reasonable? That was a lot of words, so if that was confusing, I can clarify. Okay.
In that second situation, there would be no island.
Yeah, in that second situation, there is no island because there is no bulk entropy term. So instead, it turns out that the type of reconstruction that you should think about in such situations is called state-specific reconstruction. And this was shown in a recent paper of Akers and Pennington. So let me define what this means. Okay, so according to them, the statement that should be equivalent in the more general case to having to A being the entanglement wedge of capital A and having the generalized QES formula is that if A is the entanglement wedge of capital A in the particular state psi, then for every local unitary operator U small a, which acts only in the small a region, there exists a unitary operator UA psi in capital A such that the analog of the statement that I wrote down before is true. Okay, and in particular, this reconstruction UA depends on the state psi that you have in your effective Hilbert space, and it won't be the same for all of the different psis. And in fact, we even have a no-go theorem which shows that you can't have it be true even for all, you can't have it be the same operator even for all sub-exponentially complex states in your Hilbert space. So that would be a contradiction with V not being an isometry.
So this statement here is a constraint on the state that you're giving for what state it works? Or what is it?
No, sorry, this statement should be true for every state in H effective. So this is equivalent to having a QES formula. So essentially, if
so this is the definition of reconstructibility that you're setting?
yes.
Okay.
Yeah, and in particular, it's equivalent to having the QES formula that I wrote down before for this particular state with the entanglement wedge given by small a.
But as you said, not for all. You don't expect this to hold for not for all states, right?
No, so the thing that's new here is that this reconstruction UA depends on which specific state psi you have.
Okay.
So it seems like this could have been an extremely trivial statement because this is just telling you, okay, so you have your state psi and then you act on it with some operator U, you send it to some boundary state, and then whatever V psi you have, it seems like in principle, all you have to do is send this v psi to that state, and you don't have to satisfy this condition on multiple states. So it seems much more trivial at first sight than the usual kind of reconstruction which holds for every psi in the effective Hilbert space. What is non-trivial about it is that we want some unitary operator which is restricted to some subsystem on the boundary. So in particular, if you had some non-unitary operator which was restricted to some subspace, then by things like the Riesz-Rieder theorem in QFT, you expect that you can, in principle, make all possible states by acting with that. So that would not be a very strong statement at all. But being able to act with some unitary reconstruction of a unitary operator is actually a non-trivial statement if it's on some subsystem.
Can I think of this statement as telling me what kind of code subspaces I should be looking at? The kind of code subspaces I should be looking at for error correction to work is ones where I have some effective state in the bulk and I'm acting with local unitaries. Is that roughly how I should think about it?
But even then, you would have a different reconstruction. Yeah, so if you act with only local unitaries, then you wouldn't change the entanglement structure. So you wouldn't change where the entanglement wedge is.
Well, entanglement structure between little a and little a, but in principle I could change the entanglement.
Yeah, sure, you wouldn't, yeah. Well, but if you change the entanglement structure in the other place, in other parts of the bulk, then you might create a region which, like, you might make it more favorable for the entanglement wedge to shift. So you really don't want to change the entanglement structure between different bulk regions at all. But I think even in that case, for different such states which have the same entanglement wedge, I think this reconstruction still depends on psi, even within that set. Okay, so this is the type of reconstruction that we expect because we have a situation where the QES is shifting in between different states of the effective Hilbert space. We expect that this should be the type of reconstruction that we have in this situation. Although their theorem here for these two statements being equivalent was still shown rigorously for the case where V is an isometry. So we need to show something further in our setup. And in particular, we want to write down some condition about the map and the bulk unitary, which is equivalent to this statement being true. Okay?
And you expect this to be true with some error also, right?
In our case, yes. Yeah, so in their case, for the isometry, they show that these things, like the exact version of the statement is equivalent to the exact version of the statement. But for us, yes, there should be some error. And from what I said in the beginning about how like some operators should just map a state to 0, and those operators it should never be possible to reconstruct. So there's some restriction also on the set of operators that can be reconstructed.
If this reconstruction is state dependent, then does it not make T nonlinear? Because if you take two different states, right, and take two different unitary operators and take the linear combination of these two states, and at some level, you won't get a linear combination of the vectors.
Yeah, wait, let's see. So are you saying that if U is a linear operator, you don't get a okay.
You can ask a linear operator, but what I'm saying is V is somewhat nonlinear.
V is what it is. V is given to you.
But you should be able to, if you take linear combinations of U's acting on different strings, then you should also get a linear combination of the right and left. That's not that.
I think you do get some linear combination of things on the right-hand side. Right? I don't see a.
UA is psi dependent, right? So you get something like UA psi1 acting on psi1 plus UA psi2 acting on psi2.
Yep. So in this case, you just get a. Yeah, that's right. Sorry, I'm blanking on, is this not,
Okay, this is linear, sorry.
yeah.
A times something plus B times something, you're getting 8 times the first answer.
Yeah, I think, yeah, so this is not inconsistent with linearity.
No, here's the point is that you could also compute this by taking psi1 plus psi2 as a state.
Yeah, oh, I
Then
see.
you will get UA with the superscript psi1 plus psi2.
Yeah, yeah.
Now
Yeah.
why is that the same?
So
as
then
what
you would
have
require some consistency condition, but it's not necessary that it's not linear, right?
Well, so you would get U of psi1 plus psi2 in the superscript acting on V on psi1 plus psi2. So when you expand, you will get these weird U's acting on these individual pieces is equal to those UA psi1 acting on psi1 and UA psi2 acting on psi2. So there has to be really some condition.
Yeah, that would, yeah, I agree. Yeah, you're right. There should be some kind of consistency condition, but
Is there condition that U psi is linear in psi?
That will not work. That will be quadratic.
yeah, you're saying there's some possibility that that condition would just reduce to this being independent of psi?
I mean, you don't have a good classical bulk for arbitrary linear combinations of good classical bulks.
That's true.
So
That's
where
true.
assumption should favor. Right?
Yeah.
So where exactly is it?
So some appropriate class of states.
Yeah, exactly. So you cannot quite apply this equation to the next step that I said, which is U VU on psi1 plus psi2, because that is not a classical bulk state, right? So
Yeah.
so in this statement, you should somehow constrain states to be some nice states, right? Some classical, semi-classical bulk states.
Yeah, so I mean, for our black hole setup, we will eventually say that these should be all sub-exponential states. But in principle, their prescription is supposed to work more generally, like including in cases where it's an isometry. So, yeah, I'm not sure.
But isn't there say something like, I mean, in some weird, I mean, that there's some regime of validity, and then for some other states you have to talk about some one-shot something.
That is an earlier paper by them. This is the more recent one. This is from last year, but that was from 2019, I think. Yeah, I guess in the more general case where you have psi1 plus psi2, I think it's not even obvious that that the entanglement, like that this operator would be reconstructed in the region capital A, right? It could change the entanglement wedge, and yeah. So I haven't thought a lot about that case, but that is a good point. Like I think should think about it later, but maybe it won't be so important for right now.
At the very least, you want the superpositions to be such that they satisfy the QES curve.
Yeah. But even then, it seems like there might be some kind of consistency condition if in the case where they do. Yeah, so should think more about that.
Actually, in order to talk about A being some entanglement wedge, you need the state to be geometric, right?
I think that's here it's being said that is being said by saying that there's a QES curve. Right, Shreya?
Yeah, there's some QES formula with some generalized definition of the area, which is it's just defined in terms of some entangled input state into the whole map.
Psi1 plus psi2, there may not be such a formula. Okay, if there existed one such formula for
Yeah. Okay, so let me write down the condition for having this kind of state-specific reconstruction for the case where V is some general linear map, which for this statement I'll just call L. Okay, so the statement is that for a linear map L, which goes from some Hilbert space HA to HB tensored with HB bar. So we divide the boundary into two regions. And WA, a unitary on A, and psi, some state in HA. The following two statements are equivalent. Okay, so one is an approximate version of this state-specific reconstruction statement that I just wrote down. So it says that there exists some unitary operator WB on HB such that these two states are closed. And then the second one is kind of along the lines of the decoupling theorems, if you've heard of these in quantum information theory. But it basically captures the idea that after acting with this map, the region B bar doesn't know anything about the fact that you acted with WA in the region A. Okay? And then somehow the fact that B bar doesn't know anything about it is enough to ensure that there exists a reconstruction on just B. Okay, so let me write down the statement. So and then, so the statement is that 1 implies 2 with some epsilon 2 related to epsilon 1, and 2 implies 1 with some epsilon 2, which is with some epsilon 1, which is small if epsilon 2 is small. Okay, so this second statement is basically saying that if I consider the state like the reduced density matrix of B bar after I act with W on the states, WA on the state psi, and then map this to the boundary, then the resulting state is very close to the state if I hadn't acted with WA on psi. Okay, and now this second condition is something that we can explicitly check given some definition of L. Okay, this is a statement which can be proved, but one thing that's a bit unfortunate is that it doesn't give any explicit expression for WB. So it doesn't give you something like the PETS map in the non-state dependent case, because it ends up using just it ends up using something called Ullmann's theorem in quantum information theory. And that is something which doesn't give you, it's just an existence proof of some WB.
So, I mean, can one basically add these statements saying that your linear map should obey some sort of approximate Dirichlet conditions?
Yeah, this, you mean the second one? Is something like an approximate Dirichlet condition?
Because we imply each other both.
Yeah, I think it's some state-dependent version, some state-specific version of that.
Where is state dependence coming in here?
Because this statement is in terms of, like this is, if this is true for a particular choice of psi, then this will be true for that particular choice of psi, and in particular WB will depend on psi.
Okay. So, sorry, I mean, there are two kind of generalizations here, right? One is that towards in the direction of state dependence, and the other is in the direction of it being non-isometric.
Mm-hmm.
So you said, so for there was one statement that you just said that it doesn't work because it's a state dependent construction. I forget now what was it?
I just said that you don't have any explicit form of WB.
Like Betzman.
Yeah, like it's, I mean, it doesn't follow from this theorem at least. Yeah.
But if you did not have any state dependence, kind of, if you had fixed the state,
Yeah, I think in that case,
the fact that it's non-isometric doesn't stop you from writing Betzman, approximate Betzman.
Yeah, I guess all I was saying right now is that this particular statement doesn't tell you that it doesn't tell you any specific form of this. I think there are a few cases where the state dependence the state specific nature is important, but it's still not an isometry. The map is isometric, but the state specific nature of the reconstruction is still important. In those cases, I don't know if there is something in this Akers and Pennington paper which explicitly constructs the map. Yeah, but I don't think there is, but yeah, but this should be checked. Okay, so this second statement is something that we can try to evaluate for our particular choice of L. Using this Haar average again. And then when we evaluate this, let me just state the result. So we find that if you have some operator ULR, which lives in the interior, then this can be reconstructed so remember in this in the picture that I had, I also included some reference system capital L, which was something which allowed the state on small l to be a mixed state and just purified it. So in principle, my boundary system consists of L, B, and R. And I can ask three questions. I can ask, when is it possible to reconstruct the operator on BR? And when is it possible to reconstruct on just B? And when is it possible to reconstruct on just R? Okay, so from this you find that you can reconstruct on BR when L is much smaller than B. So this is just saying that whatever you threw in initially, the dimension of the Hilbert space of the infallers is much smaller than the dimension of the black hole, which is expected for the case where you have some fast collapse to form a black hole. So this is almost always true. And you can reconstruct on just B when log L plus log R is much less than log B. So in particular, at most times before the page time, you can reconstruct operators which are in the interior on the black hole. Oh, and sorry, this is so this is all for the particular choice of the Hawking state.
In that condition number 2, there's no WB on the right-hand side. It's a trace.
Sorry. Here.
The second term,
Yeah, this is a trace over B.
and there's no WB there.
Yeah, exactly. Yeah. So this is a statement just about the fact that the state, like after you trace out B, after you trace out B in the boundary description, you lose the fact that you lose your knowledge of the fact that you acted with A.
Sorry, there is some issue actually.
Mhm.
I also feel because there you choose to look at it, right? Because you are tracing more B. Oh no, sorry, what is A?
So A is the input system.
Okay, fine.
Okay, and
So I guess the idea is that WA is reconstructed in HB, right?
yeah, yeah,
And that's why if I trace over it, then it's as if I did not, because it's a unitary.
yeah,
Okay, fine. It
exactly.
makes sense.
Hmm.
Because it's an attack.
Yeah, yeah,
So you could put it or not put it, you'd have got the same answer.
yeah, exactly. So this is just saying that B bar doesn't know whether you acted with it or not. Yeah.
Okay, fine.
Yeah, so then when you evaluate this condition, you find that, and then you find that you can reconstruct on R when S2 of psi R is much bigger than log L plus log V. Okay, so when the entanglement entropy of the radiation on the state is sufficiently large, then you can reconstruct on the radiation. Okay, so in particular, after the page time, in Hawking state, you can reconstruct interior operators in the radiation. But this statement, but now we understand kind of the regime in which this statement about reconstructing interior operators on the island applies. So it's true only in this state-specific sense. Also, so this statement is made based on averages. But again, we should see like what this implies about the case where you have some typical unitary U and not the average. And in that case, you find that you have to put similar restrictions on the complexity of both the state psi and the operator W that you're trying to reconstruct. Okay, so yeah, so now we would say that operators and states, like operators of sub-exponential complexity can be reconstructed in a state-specific way on states of sub-exponential complexity in the bulk. Yeah, so this was the main result that I wanted to talk about today. One thing that's worth thinking about is what are the operational implications of some statement like this? Because, so yeah, so what if I was in a situation where I have some,
Sorry,
yeah.
I didn't quite understand how you got those statements.
Oh, I got this statement by evaluating this average. Taking L in this second equation to be V, which I had written down before. And then V involves this Haar random U, so I get this by doing the Haar average of this quantity. For some choice of my input state psi. And then the answer ends up depending on the entanglement entropy of psi on the radiation system. Okay.
And for these errors, I guess you want the epsilon 2 to be small. And for that to be small, again, I presume something like the last lecture is true, that you don't actually need sub-exponential complexity states in the bulk. You just need a small enough set that.
Yeah. Again, the argument relies on measure concentration and so actually, this being small on average will just be true as a consequence of the average and the sizes of the dimensions of these systems. But then for the probability to be small, you would do a similar counting to last time. Yeah.
So in principle, I could look at very high complexity states in the bulk, but as long as there is a small number of them.
Yeah. and in principle, you could look at high complexity operators, but there should be some small number of them. That's right. Okay, yeah. So I guess one last thing to say about this is trying to understand what statements like this are actually saying and if they're actually useful. So what if I wanted to do something like the question Shiraz asked in the first lecture, like what if I want to create a truck in the interior of the black hole or something? Okay, so in our setup, this is a question that I have some boundary observer who wants to implement a bulk unitary ULR. Okay, so do these statements imply that there's some situation in which I can do this? Because what this boundary observer has is some boundary state psi tilde. Okay, and I said that for a given bulk state psi, I can have some state-dependent reconstruction of bulk operators on the boundary specific to that state. But now I also know that my map from the bulk to the boundary is not an isometry. So is there even some unique bulk state that I can identify corresponding to my boundary state psi tilde, which is the only thing that I actually have. Okay, so for this, it turns out that if I assume that this psi tilde has some corresponding bulk state, which is sub-exponential, then this will be roughly unique. So then so the precise statement is that this quantity is small. Okay, so this statement is telling me that if the difference between if psi and phi are two different bulk states, which are both of sub-exponential complexity, then if the distance between their boundary mappings is small, the distance between their bulk versions is also small. And this statement just follows after a little bit of linear algebra from the statement that I showed you about the inner products being approximately preserved. Because essentially you can think of both the inner product and this as some measure of distance between states. So this is telling me that I can roughly identify some unique bulk state of sub-exponential complexity psi corresponding to my boundary state psi tilde.
But here the assumption is that psi and phi both are kind of these sub-exponential.
Yeah, exactly. So this is saying that I can identify some unique psi in the bulk as long as I'm restricting to the set of sub-exponential states. And so then in principle, I can find the psi corresponding to my psi tilde, and I can find the bulk operator OB for psi with which I can do this operation of constructing the truck.
So what this says is that if you do have psi, it is unique approximately.
Yeah.
Does it also say that there exists a psi?
No, you have to be in the right. Oh, I see. Does there? No, this doesn't say that. This is an assumption.
That's an obvious thing.
I guess.
If you give me a boundary state, can't I just compute like whatever, like say Euclidean path integrals or whatever? Can't I just find the bulk state? By doing the standard radius GKPW.
You mean like I can compute its.
The boundary state is like a boundary condition, and then I can just evaluate the bulk and figure out what the bulk state is. Am I thinking of it wrong?
Yeah, that seems reasonable. Yeah, I mean, it's also consistent with the fact that the issue here was that there were many more bulk states than boundary states. So it does seem reasonable that given some boundary state, you should be able to find some bulk state which corresponds to it. But I think, yeah, what you're saying sounds like an explicit. Yeah. Yeah.
No, but you also want to get the nice bulk state, right? The sub-exponential this thing. Not just any that would be given by something given by. So, existence of such a state, you could still ask a question about or not?
It seems like from the path integral procedure that you're describing, the state, yeah, I don't know. I guess if you pick a particular reference state, then showing that any state that you construct with this path integral procedure is actually of sub-exponential complexity relative to that. I don't know how to show something like that. But
Because you want to get a nice set of state, I guess.
Yeah, I mean, usually it's going to be just some bulk geometry with some state of the bulk quantum fields, and I'm not sure why it would be high complexity. I'm not obviously able to see that it's going to be high complexity.
yeah, I guess usually the state would not have a very complicated entanglement structure between different local bulk regions. And
Yeah, as far as I can tell.
yeah. Yeah. So I guess assuming that, if you can identify such a state, then it's saying that it's unique. Yeah, okay, so that was all I wanted to say about operator reconstruction. And this might be a good place to end. Yeah.
Okay, so apparently the Zoom meeting is ended, so there is no Zoom audience. So any questions from the physical?
So does this last statement also hold for not just sub-exponential states, but for some small class of states?
Yeah, I mean, because this only relied on the measure concentration result about the inner products, which is true for a larger set of states, so this should also be true for that larger set of states. That's right.
Just to understand this last statement, is the comment that if the bulk unitary is not, is sort of mapping you within this set of, the subspace of states where the map kind of looks like an isometry, at least approximately, then you can do the reconstruction of the config. Is that what it's saying? Or,
Sorry, say it again.
so if you're trying to implement some bulk unitary LR,
Yeah.
so if that U sort of leaves you within the set of bulk states where this map looks like an isometry, approximately, then reconstruction works. Is that the statement you were trying? Then you can implement this on the boundary.
I think the statement that I was trying to make was just that it seems like the state-specific, the fact that the reconstruction is both state-specific and the map is not an isometry together seem to suggest that if all I have is the boundary state psi tilde and the fact that I want to reconstruct some ULR, which I'm assuming is something sub-exponential, then it seems in principle I have no way of doing that because the reconstruction depends on this bulk state psi, but this might not be unique because of the non-isometry of the map. So this is showing that this is basically showing that this non-isometric map is roughly invertible on the set of sub-exponential states.
So on the set of states in the bulk where it looks like this map is invertible, you can reconstruct.
Yeah. Yeah.
So when you have this non-isometric,
Yeah.
can you find an inverse map which is an isometric?
Um,
When you compose, then you get identity. And would that be useful at all to talk about?
It would be nice if you could find that. We couldn't find any way of writing down something like that.
So you mean that there does not exist?
An inverse of this. Yeah, but if you could do that, then it would be much easier to talk about operator reconstruction because then you would just say that the thing you should consider is VOV inverse instead of VOV dagger. But at least in this random unitary model, like we tried writing down a few different explicit things, but nothing seemed to work.
So in this part, and in much of the last lecture also, the radiation has not played any role, right?
The radiation was important here.
Okay, but for for this statement, for instance,
Yeah.
it might not be, right?
Yeah, here it wasn't important, that's right. Yeah, so this can be seen as a general statement about non-evaporating black holes or any other setup.
Yeah, the thing that was confusing me 2-3 lectures ago was that people used to say that you should, to create the truck, you should be acting on the radiation.
Mm-hmm.
Now, in the situation where there's no radiation, I mean, yeah, this is, I'm sorry, I have a very informed question. The question of a cause is this, that if we were just in a situation of ADS-CFT, where you know, the boundary, it's reflecting, there's no radiation, this discussion, I think, would go through.
Yeah.
You had a black hole there, and you're just trying to look at the reconstruction of the bulk in terms of the boundary. There's this bigger Hilbert space, you're trying to reconstruct that and so on. And here it sounds very reasonable. What was confusing me 2 or 3 lectures ago was that there's this parallel statement that you should be able to construct the truck, I thought, only by acting on the radiation Hilbert space. My ill-formed confusion is how are these, I mean, why is the radiation playing a role somehow?
Because what we found from here was that, so this was just about identifying the correct bulk state to act on. But this is the part which discusses where you should act in the boundary to reconstruct ULR. And so the conditions for this are given by these 2 statements, right? So this is where it's telling you that you can reconstruct ULR by acting with some UB on the black hole only when this is true. And this is true before the page time. Yeah.
I see. So in a situation where there's no radiation, this will always.
Yeah, exactly.
You create the truck by acting on the boundary.
Yeah.
And in the situation where the radiation, there's a lot of radiation highly entangled with the inside, you will not be able to create the truck acting on the boundary?
Yeah, on the boundary black hole. Yeah.
On the boundary Hilbert